Hello. Okay, this video will show you the GME driver for GDAL. So first I'm gonna say a few words about the Google Maps Engine API that this driver uses, and then we have the Maps Engine UI that I'm gonna show you, and then I'm gonna show you the driver and its options, and then I'll have a few demos for you using OGR to do the uploads and downloads. And then I'm going to show you how to use the Python, well, just demonstrate the short Python script I wrote to upload some data using the OGR driver. And then finally showing how to use GrassGIS with this driver. Alright, let's get started. So first we have the Maps Engine API. The documentation is very good. You have to set up a project and so on. It's all explained here in the documentation. The API itself is RESTful, which means that the URL requests and posts are very predictable and easy to use, and it's also very well documented. We have and then the data that you send and receive is GeoJSON, which is a nice format which is now taking flight more or less in the recent few years, and it's a really nice format for data transfer. It's not as verbose as let's say GML, for instance, and but it's as expressive as GML, so you can have your multi-polygons, multi-lines and so on. Okay, so let's have a look at the Maps Engine UI. So when you first log into Maps Engine, you have a dashboard, well, which shows you how much you have been using your instance. I don't have any maps in this instance, as you can see here it's empty. I just have a bunch of data sources which are like vector maps. One of the data sources we're going to use today is this world map, which I've downloaded from the Natural Earth Data site, which you can see here, and I downloaded the world features, the countries. So we have a bunch of countries here with a lot of information. If you look at Finland, you can see we have a ton of fields here, which is nice, but can be a bit overwhelming. Anyways, this is data we're going to play with when using the OGR driver, and yeah, okay. Let's have a look at the driver itself and documentation. So here's a very quick overview of the Maps Engine API, and then we have the GME driver itself and sort of config parameters it takes. It uses the Google OAuth 2 to do the authentication, and actually GDAL already has an implementation for that, so there was no need for me to implement it. And then we have the API key, which you need to have. You need to set up an API project in order to use the Maps Engine. Again, it's explained in the Google Maps Engine API documentation, so you should check it out there. And then we have the refresh token, which you can then the driver is made so that you can use a refresh token to authenticate through, which makes it a bit easier to do. You don't always have to then approve and go via a website and so on. You only need to do it once, and GDAL comes with a Python script, which is explained here. So you have the GDAL auth.py script, which will generate this refresh token for you, which you can then use whenever you use OGR or the driver. It takes either a tables parameter and then you can do a select or a where. It's optional. You don't need. I wouldn't recommend using the select and where. I would instead use the OGR mechanisms for selecting columns and to have this where. The driver will translate those into select and where statements sent to the server, and then you can have specify also the access token on the command line. And then to write, you need to tell which project. It's a Google Maps engine project, which you can easily find here with the CID parameter in the URL. I think it might be nowadays also listed somewhere else, but that's where I've always looked at it. So you have yeah. And yeah, it's pretty easy to use, and then you can just use OGR's functions to create whatever data you need, tables with this when you load the driver with this syntax here. Okay, well, let's have some demos. So here I'm gonna first demonstrate the OGR to OGR command with a few ways of doing stuff. So let's have a look at the first command, which will upload a simple shapefile, a very trivial one. Let's OGR info it. We can have a look at it's called simple polygon, and with the OGR info minus AL we will get all the features. As you can see, it's a very simple polygon centered around the origo of the world coordinate system. So basically, if you look at this world map here, it will be a small box-shaped donut around here. Okay, let's just upload it. I have this command here which will do that, and as you can see, it won't do any output since, well, it's the OGR to OGR command. It doesn't do any output, it will just do it. So in order to see the results, we need to go back to Maps engine here, refresh the view, and you can see simple polygon here. You can see it has 3 columns, just like we saw here. We have str call, dbl call, int call, and then the gxid also. The gxid is used by Maps engine in case you don't specify any other primary column, and it's not actually shown here in the schema. And here you can look at the data. As I said, it's a small donut, box-shaped donut, and we can see it has the str call equals bar, dbl call equals 3.450, and int call equals 11. And to check back here, you can see that these numbers are the same. Alright, so that's that. That was the uploading of the data. Now I'm gonna start downloading this world countries map with different parameters. So first we will have a look at just downloading everything. It will take a while to, well, not that long to run, a few seconds. There we go, and you can see we have the world countries shapefile, and we can do the OGR info on it. And I'm going to pipe it to less because it will output a lot of data. So here we can see, for instance, we have then the table definition, and then we start having the features. So let's look for country. Let's look for Switzerland, which we have here. It's feature number 99, and here we can see sort of data here that it has, and we can compare that to the data that we have for it here. Yeah, looks about the same, doesn't it? Well, that's because it is the same. We downloaded it. Okay, next up I'm gonna have a look at selecting the spatial bounds. So I have a bounding box of 4 degrees west, 4 degrees east, so it's just west of Norway's west coast, and then 55 degrees north, which should give us a line around here-ish. Yeah, so we should get Denmark and then the Baltic states, and then an east of 30 degrees east, which is just about here, which will give us a little bit of Russia and then Finland. So we should get the Baltic countries and the Scandinavian countries with that request. Let's see, and it should run faster now than the so it actually sends the bounding box as as part of the request, which means it's actually doing the selecting part on the server, which is very nice because we don't then need to do the selecting part on the client side. It's less data to transfer and will allow for working with larger data sets. And if we then look at the OGR info, we can look at Northeast Europe that I uploaded it to, as you can see here in the this is the data source that I saved it to. It's still the shapefile is still called the same because I did not specify to rename the layer. So we can see here we have Russia, large polygon, then we have Norway, Sweden. Actually, let's have a look at which countries we got. So I can just grep for, let's see, name, Ian. I think there's a let's see, what is it called again? Type Russian name alone. Formal Ian. Okay, so instead of piping it to less, I pipe it to grep, and I'll grep for formal Ian. And then we have here, you can see Russian Federation, Norway, Sweden, Denmark, Finland, Belarus, Latvia, Lithuania, and Estonia. So we got all the Scandinavian countries and all the Baltic states, and also Belarus, since the corner of that bounding box touched it a little bit, and that's the way sort of it works. I specified a bounding box and requested all the countries that touch that or intersect with that bounding box. Okay, let's see what other commands we have here. We can select all the countries that have the attribute continent equals Europe. So we should get all the European countries. We can do actually the same thing that we did here, but instead of in Europe we use Europe, and here we have all the countries of Europe. All right, so far so good. Finally, we have a lot of data, right? You saw those huge attribute tables that if you click here on Poland, for instance, we have too much data. So what if we want to have less data? We can easily do that. We just take then this command here, where we select the ISO A2, so 2-letter code country, the formal name, and then the admin field. And we select, we don't specify any other criteria, so basically it will give us all the countries. And this is a way to get all the, to restrict the data, to reduce it. So we can have a look at, what did we call the data source? We called it column subset. So here we have, as you can see here, only ISO A2, formal EN, admin, and then the data. All right, that shows you how to use the OGR to OGR command. Let's summarize them here, where you can either not specify any criteria, well, you get the raw data, the complete raw data. You can also receive then all this was the uploading. So here you can receive the raw data, and then we have the spatial bounding box, which we specify here, which you can then specify to limit your data spatially. You can do select, a where statement, where you can specify a specific attribute that feature must have, and you can also combine this. So we could have a spatial bounding box and then specify something else. This is useful when you want to do work with a very large data set. You first spatially restrict it, and then you can also then restrict it logically, and then you can also add the select to only select the attribute columns you're actually interested in. This is a way to work to have sort of maps engine as your data backend, and then you just sort of pick the data that you want and need whenever you need it to work with it, and then you can then upload your results later on. Okay, let's have a look at this. Then the Python script I told you about. Here we have a small Python script which I wrote, which generates sort of a plus sign every 10 degrees, starting from -80, -80, and then all the way to the other end. So basically every 10th degree should have a small plus set on it. Okay, let's just run this script. Here we can see, I can show you. So here we call the gen plus method, which then basically creates a feature with the specific, we first define a layer, well, a data set, or layer from the data set, and then we give it some fields, and when we then create new features, we have this definition of the attributes that exist that we then use, so I don't need to always specify it. So this is an easy way to create the feature, and then I just set the fields to specific values and create this multi-line thingy with the plus, so horizontal line and then a vertical line, and then add the geometry and create the geometry, and then I add the geometry here, and then I have here I ask the layer to create the feature I have specified in this function, and if that works, then every 50 features I will sort of commit transaction. That means I will push the data to the GME server 50 features at a time, which is the current maximum. And the default for the driver is to actually do this just once a second, so it won't be very fast, but it will work. And you can tweak the driver if you need to have it faster. If you have like an administrative account, paid account with Google, then you can get requests to have faster uploads and more QPS, and then with that you can then upload faster. But you need to currently modify the code. It's one of my to-do items to actually make this parameter, but that's gonna be later. Now let's have a look at the command. So the first wait here is because it's now creating the table at Maps Engine, and then the second one is now it's pushing 50 features. Every time you see the numbers change, it pushes 50 more features, and we just basically wait patiently. We're getting there, and we're already at 20 degrees. We started at -80, we go all the way to 80, and 180 and 170 actually, because we started at -170. We don't want to duplicate effort, and there, we're done. So our we should now have in data sources something called global 10D pluses, which we have here. And as you can see, it's not a very exciting data set. However, it does show you sort of an interesting as a feature of the Mercator projection, which we all know that the further north you go, the further stretched it is in the north-south direction, but it keeps the angles, so the pluses are always oriented north-south. This is a simple sort of way to do T-stats indicatrix like we have here. So let's look at the data again, and yeah, not terribly interesting, as you can see. We can click on a feature and see it has an ID. It has the longitude and the latitude, and then an ID, another sort of ID. Okay, let's then do something with this. The plan I had, and which I'm gonna try to do, is to use GrassGIS. So here I have now GrassGIS loaded. I have a background dataset loaded here, the countries from the previous demos, as you saw. We can just as a background map, more or less, to get some sort of reference for our data. So first we want to download the data from Maps Engine. So if you want to download this thing, this map, I need to find the asset ID of this, or the layer ID. So we have the asset ID here, which is the asset ID of this vector table, and this number I need to use in Grass when I want to download, well, with the OGR driver, basically. So here's the upload, download the import vector data, which uses OGR to import. And when we add our table here, you can see it actually fetches the information from the server. So it knows the name of the layer, knows the type, and it knows whether the projections match. And this is a lat-long projection workspace I have in GrassGIS, and this is then the name that it will be called when I well, import it into GrassGIS. So without further ado, let's do that. Here we can see the command running, and it's checking if it contains polygons now. Oh, this was from a previous run actually. Here we have it. It found 1224 primitives, 2448 nodes, which is these pluses, and as you can see, it uploaded them here. And the nice thing here is that I'm not running with the Mercator projection, which you can clearly see from the pluses, since they are not stretched, which is also shows nicely how actually the data is really projected properly by the maps engine. So I uploaded these pluses, I generated them as lat long. Each plus is 2 degrees high and 2 degrees wide, and we can have a look at some more detailed area here, for instance, and we can see the pluses, and as you can see, they are not stretched at all, which is a nice thing. Okay, then what do we want to do with it? Do you remember these dot indicatrixes that I talked about earlier? Let's try to reproduce those. So let's try to sort of create something similar to those from the pluses. So the plan is to first, well, we can have a look at the doc I have here. So we first imported them, then let's buffer them, and then let's sort of merge. Since we imported them, Grass will treat the horizontal and vertical lines as two separate lines, which they are. They are multi-lines, which means that after buffering them, we will have two sort of oblong blobs, which we will want to merge. We can do that with vdissolve. And then let's simplify them. Because this is demo account, it has a limit on the number of vertices. This you won't have if you have full-featured paid account with Google. Then you wouldn't need to simplify it. You could upload the raw thing. But since this is a demo account, we will do this simplification step, and then finally we will output or upload the sort of buffered plus map, or the ovals, more or less, as you will see soon. And we use the OGR or vout OGR command in Grass, which will allow you to upload or export data from Grass to any data format that OGR supports, and in this case we use GME. So without further ado, let's go for it. Here we have then the command, the vbuffer command. Here you can see the full command. Now we can simply run it, and it's very simple data, so it runs in a short time. And now you can see in the map output we have these sort of blobs, which will sort of mimic our ellipses. And next step is to then create the sort of Tissot ellipses. They are not going to be perfect ellipses, but anyway, we're going to dissolve these boundaries, so it's going to be one polygon which looks like a flower or a Finnish cinnamon gingerbread. Okay, let's just run it, and the dissolving worked. So now you see we have this, well, flower like shape, and finally we can then generalize it, and so simple parameters. I use the Douglas reduction algorithm, which is a nice one because I can then specify that I want to keep only 45% of the vertices. Then it will tweak the parameters to match that approximation. So before we do that, well, we can do it. We run it. Now we run it, and as you can see, we have this kind of rougher version of it. Let's turn off some other of these features, and we can move well, we can see the pluses underneath. Let's move them above. So now we can see nicely how the plus is still in the center, and then the general shape is sort of ellipse-ish. And final step is to then use vout OGR to export it into, we have the project here specified, we specify the format GME, we have the data source name here, and we don't specify anything other than that, so we just run this thing, and it now has 595 areas to export. Well, basically uploads it. It takes a while. This one doesn't will not use transactions, so it's gonna upload it in a not optimal fashion, but more or less okay it should be. It takes about 10 seconds or maybe 20 seconds, and we're done. So now we should have something called simple ellipses in Maps Engine. Let's have a look. So here we had the pluses, and sure enough, we have something called simple ellipses uploaded now. So I'm in Switzerland, so this time is in US West Coast time, it seems to be. But as you can see here, we have the ellipses uploaded. The reason for this gap here is because the buffering doesn't cope with something crossing the ±80 boundary here, which is a bummer, but anyway, you get the drift. These sort of work more or less as Thyssen ellipses in that you can see how it stretches the further north you go, it stretches, and even here in the in this degree you can see it stretches more in the upper half than in the lower half, which is quite interesting. So, but that's how it works with the Mercator projection. Okay, and this now completes my demo, and if you find this interesting, please post a comment, or feel free to contact me, or either through, if you know my email address, or simply by a comment, or if you know the the GDAL mailing lists. I'm basically reading the developer mails there, so if you have any questions, feel free to contact me. Thank you for listening.